So today we're focusing on the process of how do we actually, go about that whole AI thing. Because as I said a few lessons back, like this is a really iterative process. It's not just like, oh yeah, like I did AI and now I put it on my portfolio and like now I'm done. Like I'll never touch it again. AI in real life, like people will spend months, improving this aspect, improving that aspect. And we talked about that a few lessons earlier when we talked about the concept of bias versus variance. So today, I'm going to build a really simple neural network in Pytorch, show off like a few features that you might not have seen before, but mainly just quickly go through the process of like, what am I doing first? What am I doing next? What am I doing next? And as you can see, we have like a nice little list here. So that's what we're going to be going through. Now, to start off, as you can see, today, I usually don't do this. Today, first I'm importing like a few short forms so that I don't have to type out the whole thing. Usually I don't do this because like I keep on forgetting. Oh, where is data loader again? Oh, it's under torch.utils.data. I keep on forgetting that. So usually I don't like import things for short forms, but you might see this type of code later on. So as you can see, we're going to be working with the Torch classes, the Pytorch classes you've seen, some stuff that you might not have seen, working with data, some stuff from Torch Vision. So today we're going to be making the famous handwritten digits classifier. I didn't have a very particular reason for doing it, other than it got to show off some of the data processing capabilities of Pytorch, which I think you'll need later. Usually you don't work on computer vision tasks with neural networks anyways, but this is like a really simple task. So I made an exception today. I'm also going to be plotting, and this word thing, you'll see what it's used for later. So just a few library imports. First thing we're doing when we're creating, this handwritten digit classifier. Again, I'm on Kaggle. I won't explain, how to start a Kaggle notebook. I've done that before, as ever, buried in the docs. I just wanted to show you the data we're working with. We have like these little images of handwritten digits, and we're classifying, oh yeah, this is a 0, this is 1, this is a 2, this is a 7, and so on. Make sense? So we talked about how you might use neural networks for a task like this earlier. You might just take every single pixel value and set it to an input neuron, and then it eventually leads to these classes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 output classes, and in the middle you can have whatever you want. Now, usually with computer vision, you want to use something called a convolutional neural network, a CNN. But in this case, this task is pretty simple because these are like 28 by 28 pixel images, pretty small. So that's the only reason why we're doing this today. Makes sense? Any questions before we get started with the process? All right, let's do it. So the first thing we need to actually get the data. With Pytorch, it's pretty easy. So the first thing, we can just get the data from this datasets class, torchvision.datasets. Pytorch already has, common datasets, common problems. So this is called the MNIST dataset. I just pass in, where do I want it to be saved? So the file path, I want it to be saved in /kaggle/working/root, /data. So it's going to create a folder like that. I tell it, am I looking for the train data over here or the test data over here? I'll explain what this transform thing does in just a second. And by the way, if I don't already have the data loaded locally, then Pytorch will go and download it off the internet for me. So that's really nice. Pytorch has a bunch of very common data sets for us to use. What's this transforms thing? Transforms is kind of like a library that lets us go from, say, image data to like transforming it in some way that that will let us view the data as numbers. Remember, machine learning only ever works with numbers. So what transforms here does, we have this function under transforms. Transforms again is just this Pytorch class, torchvision.transforms. We have this function compose, where we can pass in like a list of different transforms, and each transform is kind of like a different operation that we do on the image. So when we get, datasets.mnist, that will be like an image of a number. The first thing we're going to do is we're going to run this function pill to tensor. Pill stands for Python image library. So it's kind of like how images are represented in Python. So we're going to convert, the image in Python to a tensor of numbers. So it's going to take like the pixel value of each image and put it here. Then it's going to convert the image data type, which just means when I get back this tensor, it's going to be images. They're from 0 to 255. So the closer you are to 0, this will represent one end of a color spectrum, like let's say black. And the closer you are to 255, that will represent another end of the color spectrum, so say white. So let's say like I had a value of 128, that might be like a grayish pixel. 0 might be a really black, dark black pixel. 250 might be like a really dark white, it might be like a really bright white pixel. Does that make sense? So this transform, it automatically takes the image and gets all the pixel values for us from 0 to 255. And then this transform converts that to a floating point number, like a decimal, that ranges from 0 to 1. Kind of like imagine the sigmoid function. That's not the function that's being used, but you can think of it like that, where it's going from this range to this range. Make sense? So that's just like an intro to transforms. You can see over here, it's loading the data, it's downloading it. And now that it's loaded, I'm going to print it out for you so you can see. So I'm printing out these variables over here, train data and test data. You can see it's a dataset MNIST. That's like the custom Pytorch class. The train data has 60,000 data points, and it was transformed by, converting it to a tensor and then converting the data type to a float. And over here we have 10,000 training examples in the test data. So that's how you might read that. Hopefully that's making sense. I'm also gonna index by like a example number. So, it's just a data set. So imagine we're selecting the first row here. And when I do that, it's going to return two things, the example data and the label. So I'm going to print these things out for you. So the first thing I printed out is the label. So 5, this is an image of the number 5. And the image shape you can see is 28 by 28 pixels. The 1 just means like it's one image, not like 2 images, 3 images, it's just one image. And when I actually print out, the data values, you can see it's a bunch of black pixels close to 0, and then, 0.992, 0.775. These pixels are like a little bit closer to white. So it's just a bunch of numbers per pixel. Is this making sense? Any questions?
Wait, could you go back up for a second?
Sure.
Visualize. So why do you? So what exactly does when you set data and labels equal to train data? What does that do again?
So this is basically selecting a tuple. It's like selecting a tuple where you have one element is data and the other element is the label. So one element is like 5 and the other element is this tensor. And when I have this tuple, if I wanted to like unpack its values, I could say, data and label is equal to this tuple. This is what we have here. That's what this returns, train data at the 0th row. It has a tuple of the data and then the label, and it kind of unrolls the two values. Make sense?
Okay. So
Good question.
Python automatically splits that up when you
Yeah,
make two things. Okay. Cool. Got it.
thanks for asking. So hopefully that makes sense. Over here, this is really messy way to visualize the data. So what I'm going to do is I'm going to use this matplotlib function called image show. And what this does is it color codes each of the values in this tensor, basically like a matrix, So I'm going to pass in the 28 by 28 portion of this matrix. And the closer a value is to like 0, it'll get one color, like black. The closer a value is to 1, then it'll get another color like white. So image show will like color code the data of each element in the matrix. Remember this dot squeeze function from earlier? It just says like take away, this dimension, squeeze the inputs into just the other two dimensions. So I'm passing in the 0th index to get rid of this 1 because I just want to pass in like a two-dimensional matrix so that image show can show me an image. And if I run this line of code, you can see here we have a 5. Now you can see like we have weird colors here, so we can pass in a color map argument, color map, and we can put in like a gray color map, or maybe gray with an A. There we go. And you can see like a bunch of black pixels here, some white pixels here, and that is the image that we're working with. Make sense? Hopefully that does. So that's the data that we're working with. Last thing, we're going to split the data into like mini batches with the data loader. Again, we loaded that up at the top from torch.utils.data. It just splits up the data into like over here batches of 32. So I'm passing the data, passing the batch size, and shuffle the data for both the train and the test data. Yay, we're done, part 1. So we just loaded the data. So the next thing we got to do is we got to pick a neural network architecture. Architecture, remember, just means how many layers, how many neurons per layer. And the most important thing here, the first thing that I did was just like randomly put in something, make it work. Quick and dirty, it doesn't matter what I'm doing, it doesn't matter like which optimization algorithm, which activation function, I don't care. Just make something that goes from input to output. So that's the first thing I'm going to do. Let's see here. So I create this class basic net because it's just a basic neural net, calling the init to get all the code from torch.nn.module. Over here, I'm using a Pytorch class nn.flatten. What it does is it takes a 2D input, 28 by 28 pixel image, and just like multiplies, just square to like a very long tensor, one-dimensional. So it just takes like, imagine each row of the image and then makes it into a long tensor with each row like stacked on top of the other. So it flattens the two-dimensional tensor from 28 by 28 to 784 pixel values, one-dimensional. Over here, I'm using nn.sequential. I think I used this last time. However, I just, used it for logistic regression. So we just had 2 layers. This time I have a bunch more layers. So the first layer is like a linear layer. Again, remember that's like a y is equal to theta times x plus like some kind of bias. You can have a bias if you want or not. You have like y is equal to theta times x, that kind of thing. That's like what a linear layer does. I'll go from a 28 by 28 input because, I'm going to flatten it out. So I need just 784 here. 28 is like, I got that, by the way, from over here. I can see the images are 28 by 28 pixels. So I go from that input to like randomly from 1 neuron inputs, 1 neuron per input pixel. So like 50 neurons, why not? Just randomly selected it. Then I have a sigmoid function. Then I go from 50 to 25, randomly selected it, sigmoid function. Then in the last layer, I go from 25 to 10. 10 is important here. It has to be 10 because I need 1 output, 1 neuron per output class. So is the digit a 0? Is it a 1, a 2, a 3, a 4, a 5, 6, 7, 8, or 9? So I need 10 output classes. But this stuff in the middle, 50 to 25, and this should be 25 to 10. I'm just randomly selected for now. Make sense? The layers? Any questions?
Just out of curiosity, what parameters would you put in the sigmoid bracket?
The sigmoid doesn't take any brackets. Sorry, it doesn't take any parameters because the sigmoid is just it's just a formula like sigmoid is equal to 1 over 1 plus e raised to the negative x. So let's say sigmoid of x.
Okay,
So it doesn't have like any settings to adjust.
okay, yeah, that makes sense.
Thanks for the question. So the only other things are I need to define a forward function. Remember, you must have this. It's a reserved thing in Pytorch whenever you're using torch.nn.module. The way I do it is I just, flatten the inputs. So I'm going to get like an input x. That's going to be like 1 image. I'm going to flatten it. So 28 by 28 to 784. Then I'm going to pass it into this nn.sequential thing, and it's going to run all of these layers in a sequence. That's why it's called sequential. So as long as I have, these parameters for the linear layers set up correctly, if I have the dimensions correct, then this should work. And with the loss here, I'm using, cross entropy loss from torch.nn.functional. I remember imported that as f. And I'm being passed like the predictions and y. So I can just do that. Hopefully that makes sense. Here's like a overview. By the way, did you know you can, once you've created a child of torch.nn.module, you can just print the instance of that child. Sorry, big words. You can just print the model so that you can see each method forward and each attribute over here, self.flatten and self.layers. It's in brackets, and I can see the value that I've set each attribute to. Cool, makes sense? Let's try out this basic model. Again, random, just start off, see what happens. So I'm going to define gradient descent. This is the same exact code as earlier. You create an optimizer using torch.optim.sgd. This is stochastic gradient descent. You can use Atom, you can use RMS prop, you can use any number of other things. Just send in the model.parameters. Remember, model creates parameters and a learning rate. Now I'm going through each x and y in train loader. So each input image and each batch of input images and each batch of labels. I get the prediction by passing in the input. This calls forward underneath the hood. I get the cost for that example, backpropagation, change the parameter values, and zero the gradient so that Pytorch can calculate gradient descent again. Sorry, backpropagation again next time. And I'm just keeping track of the cost over time in this history thing. You've seen this code before, hopefully that makes sense. And now I'm just gonna, randomly set the learning rate to 0.1 because I just want something. I'm just doing a rough and dirty implementation right now. And let's run gradient descent. It will take a bit. So it's going through all 60,000, training examples. Remember from above, we have 60,000 training examples to go through. Takes a little while. I think it's done. Sometimes the spinner just gets stuck, but I can click away. You can see it's done. So now we have done it. If we didn't get any errors here, originally I did get errors. I had the dimensions misaligned. That's a common error. Like maybe I randomly put 100 here, and then the next layer is expecting an input of 50, so that wouldn't make sense. So aside from that, pretty simple. That's all we had to do to create a neural network. You like? Yeah. So that's a pretty simple neural network. Done. Now comes for the actual iteration part. So we got the data, we just randomly, we didn't have to select any features in this case. We just had one input feature per pixel. Oftentimes we'd have to select features, but we could randomly do that too. And the first goal is just pick some random thing. Make sure all the dimensions align, and you can just, get started. It's only after that that we think, how do we optimize this model? So let's get to our visuals. Remember our visuals, the ones that I said were going to be useful? So the first thing we want to do is just, cost over time. So we're going to have X be, the number of training batches. Y is the cost history per training batch. I'm going to just plot X and Y. Oh boy, yeah. Stochastic gradient descent. You see like a random lines. I'm also gonna figure out, how do I fix that? So you can see this is really spiky. It's hard to see, like it looks like it's going down a bit, but it's hard to see a trend. So one thing we could try and do is adjust the batch size. So maybe we want a larger batch size, and then like we'd have fewer spikes. So let's see, we defined a batch size up here somewhere. Here. So instead of 32, let's say we do 64. How about that? Let's see what happens. So here, I'm gonna just rerun everything for a sec. And here we go. So already you can see it's like running a lot slower. And that's the issue. That's why we don't want to adjust the batch size. Because when we have a larger batch size, it suddenly starts to get a lot smaller, very, very inefficient. Like we could theoretically say, yeah, don't do 64, like double that still, like do 256. But some batch sizes just aren't efficient compared to others. Let's try this one. Oh boy, yeah. So hopefully you can notice like now it's running slower. So usually the best way that we want to, deal with this spikiness, it's not to adjust the batch size. So you can see, this time it did lower the spikiness a bit. I think a better thing to do might just be to average over, a few examples. So basically like, let's say 1, 2, 3, like take 3 of those spikes, find the average cost. Then the next 3, find the average cost. Then the next 3, find the average cost. That's a better way to reduce the spikes. Just when you're displaying the visual, not like when you're passing in the batches. Like don't, increase the batch size. That's not practical in all cases. Instead, just average over a few of these, individual spike points. So what I'm doing over here is I'm going from 0 to the number of points that's represented by the length of the cost history, so the number of iterations. And I'm skipping forward, in this case, 10 each time. So I'm skipping over like 10 examples from the cost history each time. So what I do is I select, those 10 batches from the start point to start plus 10. So I select those 10 batches. I sum those batches, divide by the length of those batches. That's like the average. And then I add the average cost to this array I'm keeping. Is this making sense? So it's kind of like select this group, average it, select this group, average it, select this group, average it, and go through that throughout. So now that I've done that, I'm going to create like this new X and Y plots. Hopefully it's less spiky. So you can see here, this is not good. You can see like there's no consistent learning going on. So we want to adjust a few things. First thing I'll adjust, I'll make this smaller into 32 as it was before. I'm gonna run this again. Oh, wait. One thing, make sure you reinitialize the model because it resets these parameters. So I'm gonna reinitialize the model and then run gradient descent. As you can see, iterative process. Once that is done, then I'll visualize this. It will be spiky. And I'll try and fix that by taking the average. So let's say I average over 10. Hey, now you can see like a more clear trend. Let's say I average over 50. So now you can see, okay, yeah, okay, it's working. So the cost is going down over time. Yeah? Makes sense to visualize cost over time, to see like if we've selected the right learning rate. Because remember, if we made this say 1, so 10 times what we had before, what I'd expect to see is like a steeper graph. And oops, I did it again. I didn't reinitialize the model. So it's going to keep on updating like the weights it had before. Silly me. And let's just see for a second. So you can see this time like it's much steeper descent. Yeah, much steeper. But this looks pretty good. It's still pretty reasonable. We don't have the cost going up over time. That's what we really want to avoid. No going up over time. So this, is still like a reasonable learning rate choice. If I set it to like 1,000, then that would probably have some issues. Make sense how we can adjust the learning rates and get rid of the spikiness of specifically using the stochastic gradient descent algorithm, or basically any mini batch size that's like too small. So that's the first thing I wanted to do, to adjust, and play around with the learning rate a bit. Next thing that I want to do is I want to check the performance. So, I've trained this, the value is going down over time. Let's like make it a little bit smaller too. So you can see the value is like kind of like leveling off a little bit. So what I'm going to do is I'm going to this time set the learning rate back to 0.1. And this time I didn't reinitialize the weights. So it's still like learning off of what happened the last time. It's still learning and adjusting the parameters that it had saved from last time because I didn't redefine the model. Let's visualize now. Oof, that doesn't look great. Let's see. Yeah, so it doesn't look like it's getting too much smaller. I don't know if you can see here, the values are a little bit meh, but it's like 1.6675 to 1.6475. So it's not getting like too much lower. So I'm gonna leave it now at this. And let's just like try and check the performance. So there's this entire like group of metrics that you can use to check algorithm performance. The simplest is just like, what percent of the examples did it score correctly? It's like, if the digit showed a 5, did it actually predict that the digit showed a 5? That's like the simplest thing. But there's a lot of other things that you can look up. Specifically, try searching up these words: precision, recall, F1 score. There's a lot of different, performance metrics on how well the algorithm does. There's an entire science to it. For now, we're just going to check the classification accuracy. So we want to figure out, what percent does it get correct? So now what we're doing is we're loading up examples in the test loader. So these are the test examples now. Remember, we want to train on one set of data. We want to test on a different set to see, what is the algorithm really like if it's never seen the data before. So what we're doing here is we're generating predictions from the model. We feed forward, throughout. We're running this. What it returns is a 32 by 10 tensor. The reason it's 32 by 10 is because there's 32 batches, 32 examples that we passed in at once. So we get 32 outputs, each with, that 10-dimensional output tensor, 1 neuron per output class. So what we want to do is we want to figure out, which of those neuron values, remember, we did a sigmoid function, so they're going to range from 0 to 1. Which one is highest so that we can say, okay, the neural network predicted that for this example, if the values are 0.9 for like the digit 5, then that neuron is the one that's the output. I'm going to try printing out prediction just so you can see what I mean here. I'm just going to comment out the rest of the code just so you can see for a sec. There, don't do that. So comment this out. Let's see. So you can see here, we have like over here, this is the first list of 10 neurons. So it has like 32 of these where each, has values from 0 to 1. E just means, times 10 to the, so this is like 3.2356 times 10 to the negative 6. This is the 0th, first, second output. So it's saying like this class, this image, it's very unlikely to be the digit 2 because like the value is very close to 0. In contrast, it looks like the highest values over here are like this one and this one. So this one in particular. So this is what? 0, 1, 2, 3, 4, 5, 6, 7. So it's predicting that for the first example that we passed in, the output would be a 7. Make sense?
But question,
Mm,
it also seems to have a high accuracy for the last one, right?
yeah.
So then can it like say the numbers both, or?
So in this case, what we're going to do is we're going to just round to the highest value. However, there's this thing called a softmax function, softmax activation function, that fixes that issue for us of like multiple values being very high. It makes sure that we basically scale this type of output to like a 0 to 100% probability. So each example would have like all of the probabilities of each of the examples would add up to 100 if we used a softmax function.
Okay, that makes sense.
Yeah. So in this case, I'm just gonna, randomly choose the highest value. The way I'm gonna do that is with the max function. It's gonna, figure out what the highest value is. So I do torch.max prediction. I'm setting the dimension to the last dimension. Remember, -1 means the last. So it's going to look at all of these like 10 dimensions. It's not going to look at, each of the 32 examples, which one has the highest value. It's going to look at each of these individual rows. What torch.max does is it returns, the maximum value first. It returns a tuple. The first element is the maximum value. The second element is the index of that value. So it's like, does it return 9.9174 e to the -0.1, or does it return 7? Because at the 7th index is the highest value. So it returns both in a tuple. And just like before, when we get a tuple, so we can say val index is equal to, it returns a tuple that has the value in the index. So this is what this code is doing. It's just that we don't really care, what is the value that it's returning. We just want to know, like, what is the prediction? Is it 7? Is it the digit 9? Is it the digit 0? So that's why we're just keeping this index. In Python, whenever we want to discard a value, we just like put an underscore. We're just like, yeah, whatever. I'm not even going to bother to name you. That's how little I care about you, variable. So we just throw it away. Yeah? Is this line of code making sense? All right. Next thing we do is we use the equal function, torch.eq. It just returns an element-wise equality. It just means like, is each element of the prediction vector the actual labels y? So over here we have 32 predictions. Over here we have 32 labels. It's just going to check, it's going to return like 0, 1, true or false. Is it equal to that? Are the two elements in the first index equal, second index equal, third index equal, so on and so on? So what I'm doing here is to the total correct, I'm just adding, by the way, plus equal just means, take the existing value and add this new thing. So I'm just adding to total correct. From 0, I'm adding, the number I got correct, which I get by, summing over all of these. So the number I got correct, is this. It'll reset it to like true or false. If I sum over these, they're treated as like integers, like zeros and ones. So all the ones that are true, they get a 1 value. So by just summing over everything, I'm figuring out, the number I got correct. Again, I'll print out correct so you can see here. So I get like true, false, true, false, true, true, whatever. So each of these trues is treated as a 1, and each of these falses is treated as a 0. So when I print out total correct, and I, convert it to an int, then it adds the number of examples I got correct each time. Also, I'm adding the batch size because like we're processing 32 examples at a time. So like that's the total number of examples. At the end, I just return like the total I got correct out of like the total number of examples multiplied by 100 to get a percent. So you can see here we're getting 62% of the examples right. That's pretty not great, but then again, we only just like picked a random neural network. We were just, seeing, playing around, and so on. Yeah? Any questions, any thoughts so far? All right. So that's just like classification accuracy. Another thing that I'd want to do is, if you remember back in the bias and variance lesson, I would want to check the test cost versus the train cost to figure out, is there too much bias? Is there too much variance? Is the model underfitting? Is it overfitting? So what those graphs are called, the test cost versus the train cost, they're called learning curves. I'm going to show you the code, but it's like a real big mess, and it took a very long time to figure out how to make. So if you want, pause the video, try and go through it. The basics are I got like a maximum number of examples and like an interval, which basically says, first start with 100 examples, then increase by 100, go to 200, 300, 400, until like maybe you get to 1,000 examples. And for each number of examples that I've selected, I create a new model. I select the samples I need with this weird code. You can search it up. I train on that example. So I train on that little sample I selected, 100 examples, 200, 300, 400, whatever. And then I check the train and the test cost. You can stop the code here if you wanna see, but it's just a mess, so whatever. Over here, I set, the maximum number of examples to be 2,500, and it's going to iterate in 100. So it's going to go like, okay, what is the test and train cost at 100 examples? Then 200, then 300, 400, 500, so on and so on. And it's going to try and generate a learning curve. Just going to let it run. It's going to run for a while. It's going to take a while to get through everything. But it's going to return back to me like the train and the test costs, these arrays, after all of the sample tests. As you can see here, maximum CPU power. Good thing I'm not doing this on my laptop, because laptop would have crashed by now. Eventually, it will be done. I think it's done. Hopefully it's done. Yeah, it's done. And now I can plot. So over here in red, I have the train costs, and in blue, I have the test costs. What you can see is they mimic each other pretty closely. They follow each other pretty closely, especially if you see on the left. I know it's hard to see in the dark mode that I have on, but this is like 2.315. This is 2.295. So it's like differing by like 0.01. So these are like following each other pretty closely. Now, one thing that tells me is that there's not too much of a variance issue. So it's not like, the model is great at the test costs it's great at the train costs in red, but it's like horrible at the test costs in blue. But the other thing that I see is like it's very spiky. It's not like you're decreasing the test cost as you'd expect over time. So what that's telling me is, one thing that's telling me is that I think I need to run the training algorithm, this part, the training, for more than just like one epoch. An epoch is just like one iteration through the data set. So if you remember, like when we did this multiple times, remember how like the cost went down earlier? That was because we did, multiple iterations throughout this train loader data set. So that's what I did over here to fix the spikiness. I just, added a number of epochs that it's going to train over. And all the other code is the same. I won't go through it again. You can pause to take a look if you want. And I'm going to load this up so that I can run it again. Now it's going to take even longer. As you can see, it's taking quite a while. But whenever it's done, I'm hoping that there's a little bit less spikiness. Then again, I did only select 5 epochs. I don't know if that's enough. But the key idea is, at this stage, I'm trying to figure out, is there a bias or a variance issue? Because that's going to inform, what do I do next to improve my model? So that's the key takeaway of all this experimentation that I'm doing. Is it done? Still working? Takes a while. So Do you have any questions so far about, figuring out, bias versus variance issues by making these learning curves and comparing test and train costs? All right, so hopefully you get, that's this stage of the model, that's what we should do. So now this is done, and I'm going to plot the costs a little bit less spiky, not too much less spiky, a little bit less spiky. So I probably need to run for more epochs still. But in the end, the bias, sorry, this range of costs, it goes from 2.32 to 2.3. So it's not like too big, it's like a few hundreds apart. So one other thing that might tell me is maybe my cost function that I used this cost function, cross entropy loss. Maybe I should experiment with some other kind of cost function so that I get like a wider range of costs. Maybe that might help. Anyways, that's the general process. Last thing that we're going to talk about is how do we adjust hyperparameters? So once we've actually settled on some kind of model architecture, how do we change learning rates? How do we change the regularization parameter lambda? How do we change the number of layers, number of neurons per layer? If you remember, what we do is we just like plot the cost over whatever parameter we want. So again, I'm literally going to do the same thing. I'm going to probably not explain too much of the code here. What I'm doing is I am dynamically creating the layers I want. The way that I do that is nn.sequential. It can take like what is called an ordered dict. Basically, this is like a Python dictionary, but you can't change it like once you've started it. So it's like a permanent ordered dictionary. Let me rephrase that. It's like a ordered dictionary where the order matters. It's like if you say this is the first element, then that is the first element of the dictionary. The way I create this dictionary is I passed a list of tuples. So each tuple is going to have like the name of the layer and then the value of the layer. So what I'm doing is in the input layer, I'm going from like 28 by 28 images to 100 output neurons. And then I'm going to add like a custom number of hidden layers based on like whatever I initialize this class at. So for each, L in range num hidden, so like, 0, 1, 2, I'm just going to use this update function where I can update this ordered dictionary by adding like a new layer. The name of the layer, I'm just using an f string here. You can search that up, f string, if you don't understand this syntax. But I'm just creating a name based on, L, whatever that number is. So it's like hid 0, hid 1, hid 2, as in hidden 0, hidden 1, hidden 2, and sigmoid 0, sigmoid 1, sigmoid 2. And I'm setting, the values here. So I'm basically passing in a dictionary to this update method of this ordered dictionary so that eventually I can pass the ordered dictionary to nn.sequential. Sorry, I know a bunch of fancy words, but the key idea is I'm adding a custom number of layers and finally add in the output layer. So each of the hidden layers is just 100 by 100. So I've just fixed that. I'm going to see, how many input layers is optimal for me to, how many hidden layers is optimal for me to add. So over here, we have the custom layers being created, the forward function, and the loss function is still the same. I'll show you what this is doing. So let's say I set like it to 1 hidden layer. So you have in, sig in, and hid 0 and sig 0. So this one input layer, this one hidden layer goes from 784 to 100, then from 100 to 10. I could have 2. Now you can see, I have a bigger model. So 784 to 100, 100 to 100, 100 to 100, and then, back to 10. And I could like go on and on. I could make 10 of these if I wanted. So it's just creating like a custom number of layers. This code right here. If you want to take a look, feel free to do so. Make sense?
But another question, isn't it kind of useless to have a layer that goes from 100 neurons to 100 neurons, or no?
No, because the weights and biases between these different layers, they can be different.
Oh, okay.
So you can still like calculate different relationships at each layer.
Okay.
So that's like what's what this class is doing. It lets me create a model with a custom number of hidden layers. Each hidden layer is just like 100 neurons. And then I made, again, this complicated function. I'm not even going to try and explain it. It just took me a lot of iteration and trial and error. You can pause and look at the code, but the basic idea is I pass in the number of layers that I want, and each iteration of this loop, I create like a model with a different number of layers. I train that model over like a few epochs, and then I get the train costs for the model I created, for that number of layers. I get the test cost for the model I created, that number of layers. And then, I append everything to these train and test costs. So similar idea as before, check the train and test costs over a different number of hidden layers. General idea makes sense? You can pause the code, the video, look at the code. This is gonna take a little while to train. So this is like the first layer. I'm going up to 9 layers. So it'll go for a while. Here's the cool thing about Pytorch. If I go to a new tab, I'm working on something else. You see over here, I have like this play button as the tab icon. That means code is running. When the code stops running, I'll see like there's just a K. So that's a machine learning tip for you. When your model is training, go do other work. It's in the cloud, so it's going to keep running. And you'll know when it's done based on when this play button turns to a K. Hidden tips, won't run anywhere else. So over here, it's done 6th, 7th. It's going to go up to 9. It'll take a while. Let's just leave an element of surprise. I'll just close away from this tab. But ideally, like what we're hoping to have is with different number of layers, the the train cost goes down over time. The test cost goes up over time. The reason is like the train cost goes down is because you're learning a more complicated relationship. As you can see, we now have a K, it's done training. The reason the test cost would go down is you're learning a more complicated relationship. It's easier to, predict, but the test cost might go up because you might have variance. So you might like overfit to the data if you have more layers. As ever, I just plot something. So what you can see here, a bit bizarre, is in red, we have the train costs. So after, you go from having just one hidden there to more than one, and the bias doesn't really go down. That could be because we need more epochs for the model to really like fit in to that data. Could be. You do see that there is like a difference between the train costs and the test costs in blue. That shows us a variance problem. So it shows us that our model is overfitting. And as you can see here, in the later layers, when there's too many layers, then the test costs increase faster than the train costs. Is that making sense? So that shows us like the variance issue is starting to come into play. So if I were making this neural net, what I'd probably choose is, let's say 3 hidden layers around this size, because after that it seems like the variance is going up. It is a bit spiky, so I'd probably, and like these are pretty close in the end, so I'm probably looking to change the cost function and probably increasing the number of epochs. So as you can see, it's just all iteration. You're running different tests, you're testing different things, you're running gradient descent again and again, you're training parameters. At the end, you want to save the parameters. Nice thing is in Pytorch, we have this thing called a state dictionary. It basically stores like the state of the model based on its parameters. So you can see here, I am printing, the name of the parameter in model.stateDict. So each of the layers.in, it had a weight, layers.in bias, hid_0.weight, hid_0.bias. Remember, I created these layers above. I named these, in, sig, in, hid, so on. So each of these has like a weight and a bias. And here's the actual value. We get it from model.stateDict. We get back a stateDict, index it at the specific parameter. And then I'm, printing out the size. So you can see this is like 100 by 784 weights tensor. This is a 100 biases tensor, 100 by 100 weights, 100 biases, and so on and so on. Does that idea make sense? So this model.stateDict, each parameter is just a bunch of tensors with the weight and biases values, so the parameters of the model. We can save this as, we save any other Pytorch variable. We can pass the model.stateDict to the save function. We pass a file path, and this will save the weights and biases for us. We could also save with, say, joblib, for example, to compress it. Now, if you see over here, I know it might not be visible in the video, but this state.pt, it's 700 kilobytes. So it's almost like a megabyte of data, the state for this model with 9 hidden layers. Deep learning models can sometimes have like hundreds of megabytes of state data. So it's kind of really complicated to train them. They take weeks, months to train. So that's why we want to save our state so that later on we can actually just load the state. So what we do is we just make like a instance of that class again, layernet. I defined that class earlier. Yeah, since it's a child of torch.nn.module, then it gets, some custom code like load stateDict, where I can, load what's stored in this file into stateDict. It gets passed into the load stateDict function, and it automatically goes and, configures all of these individual layers with their train parameters again. And, just this eval function makes sure everything is configured and shows us that everything's loaded. Make sense? Cool. That's it. This is what we do. We're just like, instead of adjusting, the layers as a hyperparameter, we might adjust another hyperparameter. Instead of, using the stochastic gradient descent optimizer, we might use the atom optimizer. We might always, go back to the learning curves. We might adjust the number of epochs. This is what machine learning is, doing this like a billion times over. So recap. Process the data, pick your input features. We didn't have to in this case. Just get a rough and dirty model going. Then, and make sure like all the dimensions align. That's the big issue in Pytorch. Then figure out the bias versus variance using, the learning curves, or some other method of using bias versus variance. I'm sure there are more modern ones. And finally, go about adjusting your hyperparameters once you have like a model architecture set on, after figuring out, what the right bias versus variance things are. Cool. Yeah, so you just do this for months. Yay, fun. Aren't you excited? Isn't AI great? Yeah. So this is a not fun process. I don't know if you can tell. It's kind of boring. People very rarely, very rarely these days go and train their own models from scratch. What we often rely on instead is have the researchers, they train a model for us and then we reuse that model. This is something called transfer learning. We're going to learn about in the next and final lesson of the series.